just doesn't seem right to be talking about speed without mentioning Usain Bolt, the world's fastest man. Here we have a video of him setting the world record in the 100-meter race. There it is, 100 meters in 9.58 seconds, a world record that was made in 2009 and still is held to this day. After seeing that race, one can't help but ask, just how fast is Usain Bolt? Well, we know that speed is equal to distance over time. Fortunately, the math is pretty straightforward here because he was running the 100-meter dash. So if we take 100 meters and we divide it by his time of 9.58 seconds, you can see that he had an average speed of 10.44 meters per second. Now, if we were to try to convert this over to miles per hour, it would be roughly 23 miles per hour. However, we noticed in the video that he didn't just start out and immediately get to approximately 23 miles per hour. He did this thing slowly increasing his speed over time. In physics, we call that acceleration. Specifically, it is the rate at which velocity changes. Please note this word velocity here. As you recall, velocity is defined as speed with direction. So acceleration is the change in velocity. You can increase speed, you can decrease speed, or you can change direction. Let me give you some examples of what each of those might look like. Let's take an example of acceleration increasing speed. Here we have a jet going off an aircraft carrier. This is a pretty intense increase in speed. It goes from a standstill to incredibly fast in a short period of time. The opposite of that, deceleration. That's when something is traveling at a rate of speed and it stops, as a baseball might be caught in a catcher's mitt. Finally, and I think this is one of the more difficult concepts of acceleration, is the fact that acceleration is also a change in direction. Let's take these race cars, for example. They're all traveling along at, let's just say, 165 miles per hour. They're consistently keeping that same speed, yet they're accelerating through the turns just through the whole definition of acceleration with velocity. They're changing their direction. So even though their speed is remaining the same, because they're changing direction, we consider them to be accelerating. What we're going to do next is a little bit of practice on calculating acceleration. What we're going to do is we're going to consider those examples which are only changes in speed. So we're just going to assume, for the purposes of our math here, that whatever object we're going to calculate the acceleration for is moving in a straight line. So here we have the definition for acceleration. What I've done is written this in a math equation where acceleration is equal to the final speed minus the initial speed divided by time. Quite often, we will abbreviate it. Notice I have a lowercase a for acceleration, I have lowercase s's for speed, a lowercase t for time. This notation right here, s sub f, is just our way of saying final speed. S sub I is the other way of saying initial speed. How about an example to see what this problem looks like? Here we have a roller coaster. Up at the very top, as it's starting down the slope, it's traveling at a speed of 4 meters per second. 3 seconds later, at the bottom, its speed is 22 meters per second. The question is, what is its acceleration? Well, we're going to start out the way that we always do. We're going to start out by writing our formula. Acceleration is final speed minus initial speed divided by time. What I'd like to do is have you, just as we did in our other word problems, highlight what you know. Well, you know that its initial speed was 4 meters per second. You know that the final speed was 22 meters per second. And you know the time, which is 3 seconds. What we could do is take all that information and plug it into the equation. Final speed was 22 meters per second, minus the initial speed, which was 4 meters per second. All of that gets divided by the time, which was 3 seconds. 22 minus 4 is 18 meters per second divided by 3 meters per second will give us this answer here, 6 meters per second squared. We'll oftentimes write meters per second squared just like that, meters over seconds squared. Keep in mind, as with our speed problems, getting the correct number is just as important as getting the correct unit. You'll notice because we have meters per second divided by seconds, this gives us meters per second squared. It's important that you remember to square your time unit down here. Consider this other example. A car approaches a stop sign. Its initial speed was 15 meters per second. After 5 seconds, it was completely stopped. What was its acceleration? Well, the first thing that we need to do is, as always, write our formula down. Acceleration is equal to final speed minus initial speed divided by time. Here what we're going to do is go ahead and highlight what we know. We know that it was traveling initially at 15 meters per second, and we know that at the end it was completely stopped, which means that it was traveling at 0 meters per second. We know that the time elapsed was 5 seconds. So plugging these numbers into our formula, we get 0 meters per second minus 15 meters per second over 5 seconds. So again, our final speed was 0, our initial speed was 15 meters per second, and the elapsed time was 5 seconds. This gives us the problem negative 15 meters per second divided by 5 seconds, and ultimately we'll end up with an answer of negative 3 meters per second squared. So I know that this negative can be off-putting to some people, but it's a really great way for us to initially look at an acceleration and know whether or not it's positive acceleration, which means you're going faster, or if it's negative acceleration, which means you're going slower. Hopefully you'll find that to be helpful. Okay, let's go back to Usain Bolt again. I'd like to finish where we started. Essentially, Usain Bolt acceleration can be calculated by looking at his maximum speed. Now, using slow motion photography and using radar guns, they have been able to calculate his maximum speed as being 12.42 meters per second. That's close to 27.8 miles per hour. And he attained that speed 6.25 seconds into the race. So using our formula for acceleration, final speed minus initial speed divided by time, we can plug in the numbers. We know that his initial speed was 0 because he was in the starting blocks. We're going to use this maximum speed that we have here, divide it by the time, and we can see that his acceleration was 1.98 meters per second squared. Now, how does that compare to some of the other acceleration rates we may have heard of? You know, the BMW then go from 0 to 30 and 0 to 60 in 3 seconds or less. Well, that's an acceleration of approximately 5 meters per second squared. Usain Bolt isn't quite there, but his numbers are pretty impressive nevertheless.